Good morning, everybody. Okay, so I want to quickly go over with you part of the fundamental theorem of calculus. So we already know how to do what we call an indefinite integral, and that's what you're looking at here. So we want the integral of this function right here. That's 2x squared plus 7x minus 2. And the idea behind that is that we are getting the antiderivative, also known as finding out whose derivative that is. We call that the integral, right? And we know that that answer is going to have a plus c on the end because it's somebody's derivative. So there could have been a 6 or a 12 or whatever at the end of that function, and we wouldn't have known because when you take a derivative, you throw that away. Right? So we know, again, an indefinite integral is going to have this plus c. Indefinite, we're not sure. We're not sure what the original integral was. So if we actually do this integral, we know what we get, right? We get 2/3 x cubed, 7x squared over 2 minus 2x, right? Because the derivative of 2x is 2. If you want to think about this like having an x to the 0 on it, so that you can think about it as having knocked down a power, you can. And then plus c, because of course at the end of this function there could have been a constant. What we want to talk about today is what we call a definite integral. Because we know that integrals also give us, and it's the first thing that we knew about integrals, is that they give us the area under the curve. And in order to get the area under a curve, you have to talk about from where to where, right? I need limits. I need to know, where do you want me to start this area? Where do you want me to end this area or close it out? And that's what limits of integration do for us. So for example, if I say to you, find me the area between 2 and 4, we would put a 2 and a 4 on here. Right? It tells me from where to where. So we need to know today, what we're going to talk about is how to handle those limits, like physically, numerically, mechanically. What do I do with them? I know what they represent, but what do I do with them? Okay, so again, this is an indefinite integral, no limits of integration. Once I put limits of integration on it, once I give it a starting point and a stopping point, we call it a definite integral. And this one shown from -3 to 1 means I'm going from, -3 to 1. So we can see here that we have some negative area and then some positive area, and we're going to have some cancellation, probably come out to a negative answer. Okay, so again, you know how to do this in a calculator. Today I just want to talk to you about mechanically how you flesh this out. Here we go. Fundamental theorem of calculus. This is not actually part 1 of the fundamental theorem. There's 2 parts. This is actually part 2. We're going to talk about part 1 next. Do it in a little bit of a reverse order. Okay. The fundamental theorem of calculus part 2 is called the integral evaluation theorem. Now, part 1 is actually the part of the fundamental theorem that we often get questions about, AP questions about, lots of them. It's kind of a big idea. The fundamental theorem part 2 is really just one that we use. Like I said, it tells us how to evaluate a definite integral. So it's not really anything that we ever get specifically asked about, but a rule kind of like the chain rule or the product rule or the quotient rule that we just use without really even thinking about it. Okay, so if you want to evaluate a definite integral, the first thing that we do is we treat it like an indefinite integral, right? I'm going to integrate my function just like I would if there were no limits of integration. You'll notice in calculus, the notation for a function that has been integrated is the capital letter of that function. That's kind of a general thing that they do. It's not necessarily, that's the word I'm looking for. Just because you have a capital letter doesn't mean it's an integrated function, but in notation and in rules and stuff, you will see this. So like integrate lowercase f, it grows up to be uppercase F. And then we have the plus C at the end. Okay. Once I've done that, all we have to do to evaluate the definite integral is plug in both limits of integration, but we have to do it in a specific way. It's always upper limit minus lower limit. So we're assuming that this is the integral from A to B. Sorry, I don't have that written here. Okay, so I've integrated f of x to become capital F of x plus c, and then I'm going to take that and evaluate that. I don't write it as a bracket, it's typed as a bracket, but what I would write is this. Evaluated from A to B. And what that means, this notation right here, is exactly this, that you take this upper number or this upper limit and plug it into the function, You take this lower limit, plug it into the function, and then you do a subtraction. It's upper limit minus lower limit. And what I want you to notice here, this is, I don't know why I always think of this, but when I first learned calculus, my calculus teacher said, you don't have to write plus c. And I was like, what? Why wouldn't I have to write plus c? But I wasn't a student who asked questions. I just like wrote things down and wondered to myself why, but I didn't ask. I figured out why years later when a kid asked me, why don't you add plus c when you do a definite and indefinite integral? And I was like, what? I don't know why. And we did it. Watch what happens. If you plug in a b to this upper limit, you get f of b plus c. Right? If you plug in an a to this function, when you do your lower limit, you get f of a plus c. Same constant, right? I don't know what it is, but I know it's the same. And so every time when you do b minus a, this plus c is in both quantities, and you're doing b minus a. So these c's are going to cancel out. It's really important to note here that this is a definite integral is not an exception to the rule that you have to add c in any way. When you integrate, what we're saying is two things. What's the area under this curve if there's limits? And if there's not limits, what we're looking at is the derivative of, or is the original function that we had before a derivative was taken. And if you have that, if that's what you're representing, there has to be a plus c. Okay? And again, mechanically, when we evaluate a definite integral, the constant falls out. So we're just going to get a numerical answer. It's not that the c wasn't there, it's just that it cancels. Now, notice here in the fundamental theorem, it doesn't say plus c and minus c and cancels out. AP does not expect you to show that the plus c's were added and that they canceled out. It's just something that I want you to make sure that you are aware of. Okay. All right, let's try one. Okay, so I've got the integral from 2 to 4 of x squared dx. So I want to come over here. This means I want this area right here between 2 and 4. So I already know it better come out positive, right? It's all above the x-axis. Okay, so take a second and do that integral. Give it a shot and then we'll go over it. Okay, so first thing I'm going to do is integrate x squared dx. When I integrate x squared dx, I get x cubed over 3 plus c. I'm going to evaluate that from 2 to 4. Okay. Now again, you don't have to write the plus c. I write it because I don't want to be in the habit of not writing plus c. Okay, so when I plug in my upper limit, I'm going to get 4 to the third over 2 plus c. And when I put in my lower limit, minus 2 cubed over 2 plus c. Okay, so I know my c's are going to cancel. I have a 4 cubed over 2 minus a 2 cubed over 2. And that is a fine answer. If you want to simplify, you certainly can. So let's see, that would be, what, 64 over 2, so that would be 32. And then minus 4. At least I hope. Okay. If you want to simplify, go ahead. If you don't want to risk making an arithmetic mistake like I may well have just done, it's early, you don't have to simplify unless it is what is the word I'm looking for? Oh, multiple choice, that thing, unless it's multiple choice. If it's multiple choice, there's no way they're going to show this answer. Just FYI, major pitfall here that people do. Some people are like, oh gosh, I'm never going to remember to do plus C. And so they do all their work, and they're like, I'm not going to worry about plus C. And then they do all their work, and then in the end, like a minute before they turn their paper in, they go through and put plus C on the ends of all their answers. And so I get papers where they've done all this perfectly, and then they came down here and wrote plus C after the 28. No. The plus C canceled. But people get in their heads like they start to panic or something right before they turn in a test, and they go, oh my gosh, I did an integral and I didn't do plus C. You shouldn't have. And again, we did it up here. It canceled. So that's another reason it's kind of good to get in the habit of just be aware of that C. If you don't write it, that's fine. But be aware, it canceled out. You shouldn't be adding it to the end of a definite integral. A definite integral should be giving you a numerical answer every single time. Unless, of course, the limits of integration are at numbers, which is possible. Okay, so let's take a moment and let's evaluate this integral. This is the one that is this the one we looked at earlier? I think so. Yep. Okay, take a moment and evaluate this one. All right, so first things first, again, let's integrate. So I have x cubed over 3 minus 2x squared over 2 plus 2x and then plus c. I'm going to evaluate that from -3 to 2. All right, so I'm going to plug in a 2. So I'm going to get 2 cubed over 3 minus, I'm just going to reduce this. So it's 2 squared plus 2 times 2 plus c. And then I'm going to do my lower limit. And here's where I want you to be really careful. Don't leave these brackets out. There are 1, 2, 3, 4 terms here. If you leave these brackets out, you won't be distributing this negative and you'll be wrong. Also be really careful that you have a negative that you're raising a power to here. Don't want to lose a negative. Again, a terrible way to miss a problem is by screwing up the arithmetic. I mean, it's my favorite way to miss a problem, but it's a terrible way to miss a problem. Okay. So again, you can leave it just like this if you want to. If you want to do some simplifying, you can. I'm noticing here you have a 2 times -2. Oh wait, that's minus a minus. Look at me go. So this is a 4 and this is a -4, but it ends up getting added back. Okay, so again, if you would like to do this, this is 8/3 minus 4 plus 4. Oh, there, it went anyway. Minus, let's see, -27/3, 9. So this is 9 minus 9, distribute plus 9, and then minus 4, so plus 4. Okay. So this is a plus 9, so that's an 18, 22, those cancel. So I got 22 plus 8/3, which I'm not going to go any further with. You could, but why? Okay. All right, so hopefully this is a pretty, this seems like a pretty straightforward thing to you. If you have any questions, put them in the end of the video, and we will be practicing with this and using it forever in the coming days. Have a good one, and I will see you in class.